In this video, we're going to look at descriptive measures for data. A couple things I want to go over before we begin, and that's this idea of different notations for a sample versus a population. Talked a little bit before about what a sample is. Remember, it's a subset of a population where each member of the sample had an equal likely chance of being selected. When we're talking about a sample, the descriptions we use are called statistics. We have a lowercase n to represent the size, x bar is our mean, and a lowercase s to represent standard deviation. And all of these terms we're going to go on to discuss in this video. But when we're talking about a population, those descriptors are referred to as parameters. So if you're discussing the size of the entire population, the notation is a capital N. We're discussing the mean of the entire population, we use the Greek letter mu. And we're discussing the standard deviation of the entire population, we have the Greek letter sigma. So you have to start to understand these notations. You will see them clearly on your formula sheet. If you take a look at the top of your formula sheet, we have various notations listed for you. So you can check the difference. Okay, so just keep that in mind as we go through this video. Now, in this chapter, we're going to spend time on two major types of descriptive measures. The measures of center. These are the ones you've learned through grade school, middle school. These are those measures that indicate the center or the most typical value in a data set. You're going to be very familiar with them. They are your mean, your median, your mode. Measures of variation, you may not have spent a lot of time with. These are measures that indicate the amount of variation that is within a data set. One UR, that would be the range, but a new one that will be introduced will be standard deviation. So let's start with our measures of center. The first measure of center is the mean. You know this as the average. The mean of a data set, the sum of all the observations divided by the number. So let's take a look specifically at our formula for sample mean. Sample mean, again, because I want you to pay attention to notation, is x bar. And I want you to get familiar also with how we use these formulas, because I know you know how to find an average, but you're going to see these type of symbols in other formulas we're going to use throughout this class, so it's good that you see how they're used now. For example, this symbol right here, that is a summation symbol. And a summation of xi, okay, when you see your x with a little subscript I after it, that is representative of individual data sets. So if you've got a sample size that has 5 data values in it, you would have an x sub 1 would represent the first data value, x sub 2 would represent the second, and so on and so on. This symbol means we're going to sum those data values. So this x summation of x sub I just means that you're going to add up all of the individual data values. And then, of course, we're going to divide by the number. It's a lowercase n because we're dealing with an x bar. You will never see the x bar and the uppercase n in the same formula. So because we are doing the sample, we are using this specific notation. So it's a good idea to get used to the notation now. It'll help you greatly when we come back to inferential statistics at the end of this course. Okay, so again, that's your mean. The next one is the median. The median is that middle value. Now, in order to obtain a median, the key thing here is you need to arrange the data in increasing order. So often the data is given to you, the sample that's given to you is just random numbers. So you need to put them in order first from lowest to highest. Once you do that, If the number of observations is odd, then there will be an exact median, meaning that whatever value, if you have 5 data set, suppose we have 5 data values. We have 25, 27, 29, 31, 33. There's 2 here, 2 here, and the median is the direct data value in the middle. But if we have an even number of data values, we only have 25, 27, 31, 33, the median then becomes the mean of those 2 middle values, because the median is going to fall somewhere between 27 and 31. So you need to figure out what's directly between 27 and 31. So you simply find the average. In other words, take 27 plus 31, and since we're doing it between 2 numbers, divide by 2, and that's 58 divided by 2. So it's 29, or sometimes you can look at them and just see that it's 29. So sometimes your median is a number that is not part of your data set, but if you have an odd number of observations, it is a part of your data set. And then the third one is the mode. The mode is that data value that occurs most often. So find the frequency of each. If there is no value that occurs more than once, then the data set is have no mode. In other words, if every data value is only happening one time, there's simply no mode. But any value that occurs at the greatest frequency is a mode. You can have multiple modes in a data set. So if you have 3 numbers that each occur twice and every other number occurs once, those 3 numbers are all the mode. So what I want you to do now is stop for a second, hit pause. I want you to take these 3 data sets, and I want you to find the mean of each, the median, and the mode. So take the time to do that, and then turn the video back on. Okay, so hopefully you went through and did that. So for data set 1, I got my mean to be 75.1, and I want to stop for a minute and talk a little bit about rounding. There's a general rule in statistics that states that you always write your final answers, in this case our mean, median, mode, rounded 1 decimal point further than the original set of data. So if our original set of data is all whole numbers, we would actually round to the 10th. So we take it 1 decimal place further. So when you're calculating the mean and you're trying to understand, and most of the time on the test I get very specific, and obviously my stat lab is very specific and they tell you how far to round. But if you're not given any directions, it's always 1 past the original set of data. So we take that to be 75.1. When you put everything in order, the median was 75. There was a mode in this one because we had 2 73s. For the second set of data, our mean was a little higher, 79.0. It came out to a whole number 79, but since we're writing it 1 past, we would put the 0.0 in there. The median, again, came out to 75, and there is no mode in this particular set of data. For the third set, I got a mean of 69.6. It was 69.55555, so rounded to 69.6. Median, again, is 75, and the mode is none. There was nothing that occurred more than once. So there's a couple things I want you to notice, because one of the things I want you to think about is this relationship between the mean, the median, and the distribution of the data. And when we talk about the distribution of the data, that's the shape of our data. We talked a little bit about that in chapter 2. We were looking at histograms, kind of give you the shape of the data, and we talked about bell-curved or a normally distributed data set. And then we talked a little bit about right-skewed and left-skewed. And this relationship between mean and median will help you get a better understanding of right-skewed versus left skewed data. Because I want you to notice all three of these data sets have the median in the exact same spot at 75. Now, in this first data set, the mean and the median are roughly the same. They're both falling at 75. But in the second data set, notice that the mean is a little bit more than the median. And in that third data set, the mean is a little bit less than the median. So before I move on, I want you to think about this for a minute. One of these data sets is a nice, even, normal distribution bell curve. One of them is right skewed, and one of them is left skewed. So I want you to take a minute and think about which one might be which. So when you're doing that, here's what you want to think. Think of the median as the center point. Where is that mean being pulled? Data set 1, it's not being pulled anywhere. So it would make sense that this is our normal kind of nice distribution, where the mean and the median are going to fall together right in the center. But in our second data set, that mean is being pulled toward the right of the median. So in other words, here's our median, but our mean is out here somewhere. So something is pulling the data that way. This is what we would end up with, more of a right skewed data. In this one, something, these lower values, when I say something, I mean something in the data. So see how this data set has these really low values. That's kind of pulling the data to the left. So here, where our median might be here, our mean is being pulled by these lower datas. Where data set 2 had these upper value datas that was pulling it to the right, and that's what makes the data right skewed. So here's a much clearer picture of those three differences. When the mean and median are equal, we have a symmetric, nice normal curve. When our mean is pulled to the right due to some larger data values pulling it that way, we get right skewed data. When the mean is pulled to the left due to some smaller data values, we're going to end up with left skewed data. Now, let's talk about the best measure. Often when we talk about averages of data or something, or how to describe a set of data, we think of the average. All right? A teacher gives a test, often they'll announce, hey, here's the average for the class. And then you get an idea where you fall in reference to that average. But do you ever hear about average home prices? So think about that for a minute. Usually when we hear something about home values, we think median. You hear the term median home price, median housing cost. Often that is because in a particular county where the majority of the data is going to be clustered around that median, there's going to be possibly a few homes that might be, say, out there in the millions. Those few outliers could then cause our data to be skewed, and we could end up, so if we had, let's say, 150 homes that were right around $120,000, and that's right around where our median for our data falls. But then we have a couple $2 million homes or $1 million homes. Just think about that. That could end up causing our housing value to seem much more than it really is. So for example, a small town with 10 houses for $120,000 and then one $2 million home would cause an average of those homes to come out to something like almost $300,000. Is $300,000 representative of the average cost of the homes in this neighborhood? No, but the median would be about 120,000. So there are times when extreme outliers could skew the data too far in one direction. The median ends up being the best measure for a particular set of data. So where test scores, maybe a mean is good, county home prices would probably be better represented by the median. Cost of gas over a month. Gas doesn't quite fluctuate that much, so an average or a mean would be good. Now, what about qualitative data, like hair color? You're not really looking at a mean or a median, but the mode is the best measure for any type of qualitative data, because you would have how many people have blonde hair, brown hair, black hair, gray hair, and then the most would be representative of the data, so whichever comes out the most. Income. So think about income for a second. Which of those three measures will be best? Income's going to work a lot like county home prices, where the majority of the people might be clustered around a certain amount. You have those few outliers, which are going to greatly skew the data. So income is often measured by median. Now I want to talk about measures of variation. So let's take a look at two basketball teams. This is a sample of 5 players from 2 different basketball teams. Team 1, we have a mean of 75 inches with a median of 76 and a mode of 76. Okay? Team 2 also has a mean of 75 inches, a median of 76 inches, and a mode of 76 inches. So when we look at the measures of center, mean, median, mode, these two teams look identical. But if I were to show you the two teams and show you their various heights, you might think differently. So here's what team 1 might look like, and here's what team 2 might look like. Notice they both have the same mean, median, and mode. But team 1 is all right around that 76, 75. They're all basically the same height. What do you notice about team 2? Clearly, there's more variation, which is why our measures of variation are also very important to describe data, because 2 data sets could look identical if we don't look at their measures of variation. And there's a couple things you can notice about this second team. If you took the lowest, the difference between the lowest and the shortest and the tallest, the 67 and the 84, there's a lot more variation than between 72 and 78. So we need to look at different types of measures of variation to help describe these teams and see how different they truly are. The first one is the one I just talked about, which is simply the range. The range is taking the max score minus the minimum score. The maximum observation minus the minimum. And that's it. It gives you a range for your set of data. Not something we're going to use too often, but something you need to know. So here again, the range of this set of data was 78 minus 72, so that had a range of 76, and then 84 minus 67 has a range of 17. I have no idea why I wrote 76 there when I meant to write 6. Sorry about that. Everyone's like, what is she thinking? So that's 6 and that's 17. Clearly, Team 2 had a greater range. But now there's another really important measure of variation that we're going to use a lot in this course, and that's called the standard deviation. And we're first going to look at sample standard deviation because we're looking at samples. A standard deviation basically is the average of how different each individual data value is from the mean. So when we look at our basketball players, when we talk about sample standard deviation, remember the mean was 75. So the standard deviation is going to be representative of how, on average, how far is each of these numbers from 75. Now, if you think about it, in data set 1, if the x bar equals, they're all pretty close to 75, so we should get a really small standard deviation. But over here, some of these numbers are much further than 75. So when we average the difference, we're going to get a larger standard deviation. And let's go back and look at those two formulas. We have what's called the defining formula, and we have the computing formula. And I want to show you them on your formula sheet for a second. The first one here is our defining formula and our computing formula. They both work. They both take probably just as much work because we're going to be working with small samples. I will be using, when I do it in the video, I'll be using the defining formula, but feel free to attempt and to try it with the computing formula and use either one that is most comfortable to you. There's that summation again. So notice, remember, xi represents each individual data. We're taking each individual data, difference between that and the mean. We're squaring that difference, and then we're adding up all those squares and dividing by n minus 1. Okay? Samples, we're trying to get a standard deviation here, and because the sample size comes into play, we got to subtract from 1. It is just found to be more representative when dealing with a sample. As we go through this course, you're going to hear a lot about sampling error, and then as we go through, you'll have this better understanding of why we subtract from 1. This one's a little bit different, the computing formula. A couple things I want you to notice here. I want you to notice, and this is going to come up a few times, the difference between this and this right here. They are two different values, and I want you to understand what's going on in each of them. In this first summation, this one here, we are first squaring each individual data value. Then after we square them, we're adding them together. But in this second one, here we are going to, sorry, the parenthesis was around the whole thing, I apologize. Let me just make sure I rewrite that correctly. Here, we're going to take the sum of the individual data values first, sum first, then square it. Okay, so this one is square first, then sum it first, then square it. You are going to get two different values for that. All right, so what we're going to do is we're going to find the standard deviation of these individual teams. Recalling, of course, that our x bar for both was 75. As I said, I like to use the defining formula. So what I'm going to do is, in my defining formula, if you recall, looked like this. So the first thing I'm going to do is inside, take each xi minus x bar. So I have to do 72 minus 75, square that. What does that give me? So I'll do a few of these with you, then I'm going to ask you to pause the video and do some on your own. So 72 minus 75, of course, is negative 3. When you square that, you get a positive. The reason we square it So that's going to give us a 9. The reason we square these numbers is so we no longer deal with our negative values. That's why we square everything in statistics when we're looking for differences. In this case, we don't care if it's less than or greater than. So we square the number, and then at the end, we end up doing a square root. So then for the next one is going to be 73 minus 75 squared. So 73 minus 75, negative 2 squared is 4. 76 minus 75, of course, is just 1 squared, which is 1. Again, 76 minus 75 is 1. And 78 minus 75 squared. So 78 minus 75 is 3 squared, again, is 9. So I did this first part where I took each individual value minus the x bar and squared it. Then I need to take the sum of those values. So sum them up. So we have 18, 19, 20, 21, 22, 23, 24. It looks like I get 24. So now I have the denominator. I've got the sum. So the sum of xi minus x bar squared equals 24. So to find s, I have to take that 24. There are 1, 2, 3, 4, 5 data values. So 5 minus 1. So it's a square root of 24 over 4, which of course 24 over 4 is 6. Don't forget to do the square root at the end. The square root of 6 is about 2.4. So our first team has a standard deviation of 2.4. Now what I'd like you to do is pause the video and see if you can do what I just did for team 1 and do for team 2, keeping in mind when we talked a little bit about standard deviation, are you expecting to get a larger standard deviation for team 2 or a smaller one based on what we saw in the original data? So stop the video and actually calculate. Okay, so I did get a much larger standard deviation. I got 6.2. The math's here if you want to take a look at it, but please make sure you're practicing this and you're able to get these numbers. Clearly, much larger standard deviation, and we're not surprised over this. This is what we expected. Here's 2 other sets of data that you can practice on your own. We have 2 different sets. You can calculate the mean. What can you assume about standard deviation? If you just glancing at the data set, can you tell which one has the greater standard deviation? So if you'd like to practice another one, please hit pause. I will show you the answers. I'm not going to do the calculations on this one. The other thing you can start to play around with is if you have a graphing calculator, you can enter them into your lists by going to Stat, clicking Edit, and then enter them as list 1 and list 2. When you are done and after you have them entered, you can then go ahead and go to Stat, Calc for calculate, and do what we call one variable statistic. If you do that, you'll get a lot of information. So you can certainly start to play around with your graphing calculator, but do keep in mind when you turn this stuff in for a test, when we have our first test, you will need to show me the calculations on a piece of paper to get full credit. So you can use the calculator to check yourself. So go ahead, hit pause, and then come back to see these answers. So once again, just to show you another example, both data sets had the mean of 50, but clearly data set 2 had the much larger standard deviation. Here's another way to depict a visual of standard deviation using a dot plot. So if we take data set 1 and we plug it onto our graph, what I've done here is now shown. So data set 1, let me just go back 1 second. Sorry, I keep hitting the wrong thing here. Data set 1 had a standard deviation of 7.4. So this is an interesting dot plot that shows standard deviation. In other words, I think it had a standard deviation. Yeah, 7.4. So this one down here is actually data set 1. And this one up here is data set 2. So this one had a standard deviation of 7.4. So when you go from 50, notice when you add 7.4, you add 1 standard deviation, you get a 57.4. If I add another 7.4, which is 2 standard deviations, it brings me to 64.8. And then when I add a third one, it brings me out to 72.2. You can see the data is much clustered, small. It's clustered around that 50. In the second data set, my standard deviation was 14.2. So now when I add 1 standard deviation, I'm adding a much larger number. So it's bringing me out to 64.2. Or if I subtract 1 standard deviation. Okay. And then if I add a second or subtract a second standard deviation, it brings me between 21.6 and 678.4. When I do that third standard deviation, it's between 7.4 and 92.6. We talk about these number of standard deviations. One of the things I want you to notice in both data sets, even though one is more spread out than the other, the majority of the data is, or all of the data in these cases, is falling within 3 standard deviations of the mean. And that's going to occur with any data that is normally distributed. It's going to fall, a certain percent is going to fall within 3 standard deviations. And this idea of breaking our data into the number of standard deviations is something that's done a lot in stats. So I just want you to get a nice visual of that. And that brings us to the last thing I'm going to do in this particular video, which is to talk for a second about the empirical rule. Not only can we say there is a rule that states that 68% of the data is going to fall within 1 standard deviation, 95% of the data will fall within 2 standard deviations, and 99.7% will fall within 3, or the majority will fall within 3 standard deviations. This is known as the empirical rule. And you kind of saw it here. So when we talk about 68% of the data, what does that mean? Well, these data sets have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So around 6.8 or 6 to 7 data values should fall within 1 standard deviation. Let's take a look. I've got 1, 2, 3, 4, 5, 6, 7 to 8. So around 7 data values. Look at the other one. So I have 1, 2, 3, 4, 5, 6, 7 data values are within 1 standard deviation of the data. Here it's a little bit more, because that one, and it falls, looks like it falls directly on it. 1, 2, 3, 4, 5, 6, 7 data values are falling within 1 standard deviation of the data. I mean, this isn't going to be exact. It will be approximate, so you may get that 8th data value falling in there. But this is a rule for any normally distributed data. All right? And then 95%, so you could expect to see almost all the data, and we can see within 2 we have all but 1 data value and falling within 2. So that's our empirical rule. You should know these values, be used to them. And for example, if a data set has 50 observations, approximately how many will fall within 2 standard deviations? Just go to your empirical rule. That's 95%. What is 95% of 50? So again, sorry, 0.95 times 50. We should get about 48 data values within 2 standard deviations. The data set has 250 observations with a mean of 100 and a standard deviation of 16. Approximately how many observations lie between 15 and 48? So the mean is 100, right? And we want between 52 and 148. So you have to ask yourself, is how many standard deviations is that? So 148 minus 100 divide by 16, that's going to be 3 standard deviations. So how much of your data do you expect to fall within 3 standard deviations? I would certainly expect 99.7% according to our empirical rule of 250. So almost the full 250 data values, about 249 to 250. So we're going to stop this video right now, and then in the next video I will continue with chapter 3.